everyone. Thank you for the introduction, Jeremy. So I'm going to be talking to you today about my experience on the AI4SD summer internship. So not just the project I did, but the experience as a whole and how it helped me develop. So just a quick introduction to myself so you can sort of see where I am at in sort of my academic path. So I did an undergraduate dissertation project with Jeremy, looking into the modelling of solubility. And I'm currently doing a postgraduate research master's looking into using computational techniques to predict the effectiveness of antibiotics that I gave a talk on Tuesday. So a brief overview of the internship and sort of what I did. So they had some really good Skills4Scientists seminars that were attended on sort of a weekly, bi-weekly basis. And these were really good. So these are sort of on e-chemistry, so how we use computers to help aid chemical discovery, and also sort of on the more sort of stuff they don't teach you in lectures, so sort of networking and careers and more the sort of softer skills as well. So along with it, after I completed the project, there was also a poster seminar where there were academics and industry professionals, and we got to present our findings of our research and have some talks to them afterwards, which was all handled virtually during COVID, which was done very well. So why are we looking into this problem? So this is going back to why are we actually going to curate this data set? So there are inconsistencies between structural representations and chemical identifiers within databases. And if this is the case, then how many inaccuracies exist? So how many inaccurate IUPAC names or InChIs are just assigned to the wrong compound or maybe incorrect, and how would you check this? So there was some work done by a few people in this room. I think Simon and Nikki worked on it, where they used some RNN models to try and predict this, and these models worked really well for organic compounds, but not so well for inorganic compounds. So it was starting to create a data set in order to look into this problem. So a bit of chemical vocabulary, so you can understand sort of the research that I did. So SMILES are simple molecular input line entry systems, and these are just easy ways for both computers and humans to understand what chemical structures look like, because you obviously can't use the pictures. And for this research, it was important to use canonical SMILES to try, as this was a problem of inaccuracy, so we wanted to make sure that every step of the way we made sure everything was as uniform as it possibly could be. We use smarts queries, which is a way of looking into substructure of SMILES, and this is how we got inorganic compounds from all the compounds that were available on PubChem. And InChIs themselves, for those unfamiliar, they're a bit like SMILES in that they contain chemical information, but they're really mostly good because they're machine readable and not so good for humans, but they contain a lot of structural information. And we were looking into, for this particularly, the difference between InChIs and Reconnected InChIs, so this gave us a bit more information on connection between the organic section of molecules and the inorganic section of molecules. We thought this might help. So a quick introduction to IUPAC names for those unfamiliar. So it's a way of standardizing names of chemicals. So for example, the nice spinning ferrocene here would be, in IUPAC terms, cyclopenta-1,3-diene iron 2+, so very catchy. So a brief overview to the work that I actually did. So we downloaded the PubChem SDF file, publicly available data source from online, and you can download it. And from that, we used the smarts queries that I've already introduced to split this up into not just inorganic, organic molecules, but there's a few sort of crossovers between them. So you had the pure inorganics, which were just the inorganic molecules, and you had the organometallics, and then you had just mixtures of the two compounds. So organic containing molecules with metals attached. And in this process, it's quite interesting to see, and it might be why the training on the previous model wasn't as good as hoped, is because there was only 1.2 million of these inorganic molecules in the database, which shows how many more organic molecules there actually are. I'm going to go over this because I want to get on to sort of the experience of the internship itself. But this is just a rundown of how I actually went about doing this. So this was done in Python because, as I mentioned before, it was 14 million files, which just wasn't computable in many other ways. So we use the OpenBabel library to convert these SDF files to canonical smiles and the IUPAC names. And then we use smarts queries to search for things like, does this molecule contain any organic atoms that contain any carbons or nitrogens? And if it doesn't, it was defined as like a pure inorganic molecule, for example. And we run multiples of these smarts queries to try and catch edge cases, but this was sort of a go through the process and repeat until we got it as optimized as we could. And then the canonical smiles were then converted into both the Reconnected and the normal InChIs, and these were outputted as very, very large text files. And there's just the link if you're interested in where the SDF files are actually located. So what were the problems? So this was my first time working with data on this scale. The compounds the data sets I worked for before were in sort of the thousands, hundreds kind of range, and this was the first time it was something that I couldn't really process at all in Excel, which was an interesting challenge. So one of the challenges about this is because we were working with all the molecules on PubChem, smarts queries to catch edge cases was required, and this was quite a long process that required a lot of sort of refining, repeating sort of processes. So the other problem with this is that when there was an error in converting these InChIs to smiles or from the SDFs to InChIs in OpenBabel for whatever reason, the entire script would just crash, which was very annoying when you sort of spent 6 hours processing it just for one molecule to sort of destroy your entire day's work, which wasn't the best. So we wrote exceptions to this, but that came with the annoying caveat of having to write another Python script in order to clean this data again. As I mentioned, these scripts took a very long time to run, and when they crashed, sometimes I'd run it for a day and it had gone. So we eventually worked out that it's probably better to do this in batch. So rather than going back to the start and restarting the hours of computational demand, we'd split it up into batches of 500,000 molecules in a for loop in Python. And this worked really well and saved a lot of time. So now it sort of comes to what I got out of the project. So this, as I mentioned, the first time I couldn't handle the data in Excel, which I kind of used as a bit of a crutch in my undergraduate project. So all the work had to be done in Python, which was a really, really good learning curve for me. And problems like the amount of time it took to run these scripts was another interesting problem, in that there was sort of a consequence to if something went wrong. So it was interesting to learn sort of the workarounds to that. The other side of it was, as I mentioned before, the sort of the career skills you got from it. So it was really interesting going to these seminars. We got the opportunity to speak to a lot of interesting people in science, people coming into science later in life and how they got there, people leaving science and going to do other things. It was just really interesting to get their sort of perspective and their stories. And as I mentioned, these scripts took a long time to run. So I got a lot of practice developing coding skills for these big data kind of problems. And also it gave me a bit of time to read up on sort of the general architectures of machine learning, which was quite cool. So conclusions, as this is a A4SD network, I tried to make the data accessible that I spent all this time producing, so it's on my GitHub. And if anyone has any questions about it and wants to use it for any models, they're more than welcome. Get a lot of professional development through this, speaking people, especially during COVID. It was really nice because I graduated during COVID times. It was really nice to go out there and be able to actually speak to people, fellow undergraduates from different universities, getting their experience. And finally, working with experienced researchers was a really interesting insight into how they sort of work, and yeah, gave me a good overview of what research is like as a whole. So yeah, if you see anything out there that the AI4SD are doing, if they're doing any more summer internships, I'd definitely recommend. So yeah, thank you for your time.